Alright people, let's do this. Let's consider n identical molecules confined in a volume V in equilibrium at temperature T. Now let me first use a case where there are no interactions between the particles and no other potentials are present. So basically this is an ideal gas. The only energy that these particles have is their kinetic energy. Therefore this is the Hamiltonian. And if all the masses are equal, because we said that they were identical, then the masses come out of the summation. They are just constant. We're going to describe the macroscopic properties of the system by studying the microscopic properties of the particles making up the system. The problem consists of finding the partition function, and from the partition function you get all the thermodynamics of the system. So let me use the definition of the partition function. This little dw tells you that you are integrating with respect to a volume in phase space. In other words, you are integrating with respect to some coordinates q and their corresponding momentum p. You can use the n-particle partition function right from the start, but I will use the one-particle partition function because it just looks easier, and then later I can use this to find the partition function for the n-particle system. This cube here and here are just dimensions. Because we're talking about volume, then we should be integrating over 3 dimensions. And of course, we have 3 components for the momentum. My limits of integration depend on the container. For example, if it's a rectangular box, then it makes sense to use Cartesian coordinates. And if it's a cylindrical one, then cylindrical coordinates must be used. But notice here that my coordinates q do not appear in the Hamiltonian. So this integral here is just the volume. But what are the limits of integration for the momentum? Well, in principle you are integrating over all possible values. Therefore, it should be going from negative infinity to positive infinity. Now this integral we can do it like this. And of course, some people might wonder where this comes from. Well, this p square is really px square plus py square plus pc square. But this is just a change of variables. In the same way that sometimes you integrate x, y, z, and then you change variables to integrate over r, theta, and phi. So it's just the same. So let me put the limits of integration. Now notice that the angular part will give me 4 pi. So now the problem is the integration with respect to p from 0 to infinity. You will see this kind of integral very often, so write it down. So using this integral we get this, and a little bit of algebra, and now voila, the one-particle partition function. So let me explain the plan one more time. You get the partition function from one particle, then you go from one particle to many particles. This will give you the partition function of the system. Once you have it, then all thermodynamics can be calculated from this. So how do we do that? With the Helmholtz free energy. This is the connection between the microscopic world and the macroscopic one. So let me keep this formula right here on this little whiteboard. Replacing the partition function of the system into this equation will give me this. Now we separate this. Here we're going to use an approximation. This one is one of those things that you want to write down because it will simplify your life. You will see it many times. This quantity here will appear very often too. This is known as the mean thermal wavelength. You might recognize it if I write it like this. Then the Helmholtz free energy is just this. And ln of this minus ln of that is just ln of this divided by that, and that's it. You're done. From this function, any other thermodynamic function can be calculated. Let's take for example pressure. This is just a simple derivative of this function a. Derivative with respect to volume, taking n and t constants. Then the pressure becomes nkt over v, and this obviously is the equation of a state for an ideal gas. So we have derived the ideal gas law. Well duh, we started with an ideal gas, we're supposed to get that. Before I go, I wanna say a few things about the mean thermal wavelength, because sometimes We calculate things by brutal force of mathematics and we forget to take a moment to see what the physics is actually saying. So let me talk about this just for a moment. The mean thermal wavelength is roughly the average de Broglie wavelength of the particles in the gas. This is why some books prefer to call it thermal de Broglie wavelength, because it also depends on temperature. As an approximation, the average distance between particles in the gas can be calculated as the cube root of the total volume over the total number of particles. When the mean thermal wavelength is much smaller than the interparticle distance in the gas, then the gas becomes classical. It's a Maxwell-Boltzmann gas. But when the mean thermal wavelength is about the distance between the particles in the gas, then the effects of classical mechanics disappear and we have to treat the problem with quantum mechanics. Notice that this happens if I lower the temperature. Most books prefer to write this condition in terms of the particle density. So that's it. Thanks for watching, guys, and good luck.